Okay, hello everyone. Welcome to our Asian Graphics webinar session 31. So I'm the session chair, Zhao Pengcui from Zhejiang University. So today we are honored to have two excellent researchers. One is from University of Hong Kong, Xiaojuan Qi, and the other one is Edgar Simon Sari from Waseda University. So the first talk will from Xiaojuan. So let me introduce Xiaojuan Qi first. So Professor Qi is an assistant professor in the Department of Electrical and Electronic Engineering at the University of Hong Kong. She received her PhD from the Chinese University of Hong Kong and has conducted research and academic exchange at the University of Toronto and University of Oxford and Intel's Visual Computing Group. I think many of our audience know Xiaojuan's works. Actually, he has many publications on embodied agents. And recently, as we all know, that she has published over more than 100 papers in the top conference across from computer vision, graphics, and machine learning. Recently, Professor Qi received a Best Paper honor mention at SIGGRAPH Asia and was named one of IEEE's top 10 to watch in 2024. And she actively serves as academic community, frequently as area chair for ICV, CPR, NIPS, SML, and HY. So let's welcome Professor Qi for his excellent talk. Okay. Time is yours.
Yeah.
I will stop my share. Okay.
Yes. Thank you, Zhao Peng, for the introduction. Okay. So does my screen clear? Oh.
Yes, it works.
Okay, let's start. Okay, thank you for the introduction. So I would be very happy to be here to present some works in my group for 3D spatial intelligence. So in this talk, I will talk about from perception to comprehension and creation. So actually, I have worked in these areas for more than 10 years. So as we all know, 3D is very important to both all humans and a variety of agents. If they want to interactively interact with the 3D world, they must be able to understand and reason in a 3D environment. It's a key capability for these agents to navigate in a 3D world and be able to manipulate 3D objects. So this motivates me to study these topics. My research goal is to enable machines to be able to perceive, understand, and interact with the 3D world. So mostly from the perspective of a computer vision researcher. So we focus on three basic tasks. The first is about 3D perception and reconstruction. This is about how can we get 3D from images and videos. And the second is about understanding and reasoning. So how can we develop algorithms that allow machines to be able to interpret a variety of objects, their functionalities, semantics, all these 3D objects. So this is also a very key step for building intelligence, especially in the 3D space. And beyond the perception and understanding, another research aim in my group is to focus on 3D synthesis and simulation. So we would like to allow machines to be able to create 3D objects, 3D textures, and so on. So in the following, I will introduce some of my works in these three topics. So firstly, let's look at 3D perception and reconstruction. So the goal here is we would like to develop algorithms that will ultimately help us to develop algorithms that can perceive the geometrical structure of the 3D world from images and videos. For example, we may need to interpret this is the depth information from images, or we would like to have the 3D world from images. So actually, I have been in this area for a long time. So when I was a PhD student, I studied this depth from images task. So the task is that given images, we would like the model to be able to infer the depth information. So this depth information actually measures the distance or pixel to the camera plane. So this is a very typical regression task, right? So a very straightforward idea might be, let us pick up a neural network and to construct a regression objective to give an image, taking images as input, and then we can produce the depth output, right? So however, when we closely look at this problem, this depth information actually is a projection of the is the projection, one-wheel projection of this strata 3D world. So the values of this depth map is really constrained by its neighborhood values. So in this work, we explored whether the geometrical constraints from the real world can help us to develop better algorithms. We would like to allow the models to estimate accurate depths, but also we would like to make the depths to more reflect the real-world geometrical structures. So in this work, we employed an auxiliary information, is a normal information. This normal information actually will reflect the planary properties of different areas in the images, and the depth and the normal are essentially constrained by each other. For example, given this depth information, this surface normal can be easily figured out. And given this normal information, then the depth distribution are constrained because for pixels in a plane, their depths will follow a certain distribution, right? So in this work, we incorporate the geometric constraint between depth and the surface normal into the model design to see whether it can help us to get a better depth. Especially, we would like the depth to give us better 3D. So actually, after doing this work, we actually found that with this geometrical constraints, we actually can not only have better depth, but also if we project depth into a 3D point cloud, the reconstructed results will be more consistent with the real-world structures. Like you can see, these plans will be more consistent as the ground truth from Kinect. Okay, so this approach is from a direct regression approach. So I would like to say here, so if for depth estimation, this type of tasks, what we care about is not only how beautiful this picture depth image is, but also how good this depth image can be represented into 3D to really reflect the 3D structures of objects and the scene. So in this work, we found that this 3D, the geometrical constraint from the real world can help facilitate to help us to get depths that can better reflect the real world structures. And this is more results from the outdoor scenes. So these are the results from baseline approach. This is from our approach. Okay, so this work is about how can we get 3D from a single image, and another approach that is more similar as a human way to perceive 3D is to use stereo parallel images. So we also explored this area. So for all the depth estimation problem, a very critical question is about the data. So if you look at a variety of these data sets, you will find that many of the depth information are not very accurate. If you align the image with the corresponding align the depth image with the corresponding ground truth image, it is actually not aligned. We have done an experiment on Kitty. Actually, for the Kitty data set, the ground truth and the corresponding image is not well aligned. And also, collecting such data is also often take a lot of human labor and money. And even though we can put so much resource on data collection, we still cannot get very accurate results. So in this work, we are thinking about whether the accurate depth information from like computer games. This is the image from the GTA computer game, and you can see this depth information is very, very accurate and is well aligned with the image information. So in this work, we are thinking about whether this synthetic data from computer graphics engines can serve as a good data source for us to obtain better models. So a very natural question in this part is the domain difference, right? So actually, in this work, our initial study using synthetic data to train a stellar matching network already achieved very promising results, but we still find this domain gap, domain difference between synthetic and real data will cause some issues on generalization. So in this work, we have also made some innovations on the network part. So the first part is that we introduce a domain normalization layer to normalize the data so that the training data and the testing data would have more closer color distributions. And another layer is the cost aggregation module that encourages the model to pay more attention to the global and shape level information instead of focusing on the tiny details. Because when you look at the scenes, if we look at their global shapes and from a global view, they would be mostly similar. But when we look at the tiny details, they are dramatically different. So this global information can also help us to train models on synthetic data set, but generalize well on real world data. So this is some results. So this is the input video, and this is the results from a very classical unsupervised by doing optimization, this SGBM approach, and this is from previous approach that are trained using ground truth from the Kitty data set, and this is the result from our approach. You can see when we compare with the model that is trained on real world depth data, you can see these boundaries are not so clear, but for our model, the results are very clear and the performance is also much better. So far, I have introduced how can we get depth information from images. So the next part is that if we have multi-view images or scene or object, how can we obtain a 3D reconstruction of this scene or the object? So for this task, this representation becomes a very critical issue. So as we all know, this Gaussian splitting works very well for rendering no-view images for representing 3D scenes. It often works by optimizing a set of 3D Gaussians to make these 3D Gaussians to be able to fit the training wheels like here. So after optimization, the scene is represented as a set of 3D Gaussians. So this representation is super great because it can offer no-view synthesis results with a very high quality and real-time rendering speed. And also you can see this through Gaussian rasterization, the rendering quality is super high, right? But when we look at closer about the underlying geometry that this representation can offer, it is very noisy, right? So this is because these Gaussian representations are essentially unstructured local representation, and the optimization objective is only to optimizing this photometric accuracy. There is no underlying constraint on the underlying geometry it can recover. So after optimization, this Gaussian splitting algorithm can only give us very noisy 3D geometry information. But a good 3D representation should be simultaneously capture good geometry and a good appearance, right? So in this work, we are thinking about whether we can find a new representation for 3D so that we can simultaneously get a good geometry and also have the advantages of this Gaussian splitting that can have a high rendering quality and also real-time rendering. So in parallel to this Gaussian representation, there is another representation called implicit representation. This representation uses a neural network to model the 3D scene. So given a query point, this network will output the geometric attribute. For example, this SDF value. This can this representation is actually a global representation. So for this global representation, a very nice property is that it is very easy to incorporate the geometrical constraints, and it's also demonstrated empirically that this representation can deliver high-quality surface reconstruction results, like you can see this result. So this implicit representation has shown to be able to reconstruct a high-quality surface. But this representation also has some drawbacks. Its rendering speed is very low, and also the rendering quality is not that satisfactory as Gaussian splatting. So this inspires us to think about whether we can combine the best of the both worlds, that we can use this neural implicit surface representation to represent the geometry and use the 3D Gaussians to model appearance. And the rendering part is still done by the 3D Gaussians, so we can still have the speed and the efficiency of Gaussian splatting. So after we have this idea, the implementation becomes clear. We have the implicit function. So this part is utilized to represent the geometry of thing, and we have the 3D Gaussian that is utilized to model appearance of the thing. And the core component for this representation is how can we link them together. That is, how can we make this 3D Gaussians to be aligned with the SDF field. So in this work, we have actually explored many strategies, and we find that this we call it a loose coupling strategy works well. So this idea is also very simple. We just use this the implicit surface from the surface from the implicit function to control the distribution of Gaussians. This is done by making the Gaussians to be close to the surface, and also the direction of the Gaussian is aligned with the surface normal from the SDF field. So by doing so, we can make these 3D Gaussians to be aligned with the underlying surface, and it can also allow the optimization of 3D Gaussians to help optimize this SDF field. But as the 3D Gaussians are only sparse, are very sparse in space, but this SDF field is continuous across space. So in order to optimize this SDF field, we also bring back the volumetric rendering to use this SDF field to use this to render depth and surface normal. So this rendered depth and surface normal is compared with the depth and normal from 3D Gaussians, and we have the consistency objective to make them to be consistent with each other. So after this optimization, we can simultaneously optimize this surface implicit function and also the 3D Gaussians. And this implicit function is for geometry modeling, and the 3D Gaussians is to focusing on fitting these details, and they are naturally aligned. So let's look at the results, especially on the reconstruction results. So the top rows are a line of portraits focusing on non-Wilson size. You can see typically they deliver very high PSR results, and the middle rows are a line of portraits focusing on surface reconstruction. You can see generally their rendering quality is sacrificed. So overall, our approach simultaneously achieves high quality rendering and also high quality surface reconstruction. So let's look at more results. So this is the surface reconstruction result. This is from our approach. So you can see compared with other approaches, our approach achieves recovers the details, but also maintains the required level of smoothness for the surface. Because for example, you can see here, for the 2D GS-based approach, they will reconstruct many noisy surface. That is not this is not what is this underlying true geometry would reflect. And also our approach achieves detailed reconstruction, but also it maintains the smoothness and is free from noise reconstruction. Let's look at the more results. So this is the results from the MVS dataset. Okay, so our representation can not only reconstruct object level scenes, but it can also be applied to reconstruct scene level, to do scene level reconstruction. Like you can see here, the recovered surface is still has a good quality. So when we go into this scene level reconstruction, the next problem we would like to explore is that whether we can decompose the objects in the scene so that we can make an interactive scene. So in this work, we are exploring whether we can extract the individual instances in a reconstructed scene. But this task actually requires us to have the object masks across different views to train this model so that individual objects can be extracted. But obtaining these object masks is very time-consuming, right? We need to annotate objects across different video frames, and a lot of tracking and a lot of post-processing to get masks across consistent masks across different views. In parallel, at that time we have the segmentation engine model, right? That can do segmentation automatically to get and in an open world manner that we can use that leverage it to segment any object. So in this work, we actually will bridge combine reconstruction with this segmentation engine model to achieve this decomposed reconstruction. So in this pipeline, we do reconstruction. We can reconstruct the 3D scene, but we also allow each of the individual objects can be extracted, can be decomposed from the scene. And these decomposed objects can be applied with other, can be combined with other approaches, for example, to add new textures on top of them, and then or to reconfigure these objects to create a new scene, and so on, to allow a lot of applications that are requiring individual objects to be extracted and to be interacted. So let's look at the basic pipeline for this. So firstly, we will do reconstruction. We have the colored mesh here, and this is the reconstructed surface. So in the first step, in the reconstruction stage, we also distill this the segmented engine feature from the encoder on the feature field of the reconstruction. And then in the decoding process, we will leverage the decoder of the segmented engine model to extract individual objects. So after this, these objects can be removed from a scene, can be edited by users, and new objects can be added to the scene, and the corresponding textures can be attached, so that we can allow this reconstructed scene to be interactable after it's reconstructed. Okay, so far I'm talking about the reconstruction. So for the reconstruction, actually a very important issue is about the representation. After we have the 3D scene, the next task is how can we understand the 3D scene, right? So in this long research, our focus is to enable machines to translate these 3D visual inputs into semantically meaningful interpretations of the 3D world, like their relationships, their functionalities, and their semantics. In this topic, we have done a series of works. We're focusing on both model and the data. So because of 3D data are different from 2D images or videos, they are irregular and they are unordered. This causes a lot of difficulties for processing this 3D data efficiently and effectively. So in order to resolve this issue, we have proposed different approaches based on position adaptive convolution, stratified transformer, and sparse pooled convolution to optimize the efficiency and effectiveness of 3D data pre-processing. So after we done this research, we actually found that the model design often determines the efficiency and the effectiveness of data fitting, but the data actually determines the upper bound of the model. So recently we have switched most of our research focus on how can we handle the data issue for 3D understanding. So we would like to design models that can break the bottleneck of 3D data and annotations. So in this part, we have done many works. For example, we have proposed this unsupervised domain adaptation approach that can allow the model to train on one type of LiDAR data, and the trained model can be generalized to handle another type of LiDAR data. And in this work, we have explored using synthetic data and by bridging the gap between synthetic and real data, we can obtain models that are trained purely on synthetic data, but are also generalized well on real data. And most recently, we have explored how can we equip the models to be able to handle open world semantics. So in the following, I will introduce these works in detail. This is called open world 3D scene understanding. So as we all know, if we train a model on a fixed set of vocabularies, and then we put the model into inference, it can only be capable of recognizing these labels scene during training, right? But if there are a new class, like the bookshelf here, exists in this data, the model will fail to recognize it. So in this work, or this open world task, it aims to train the model on a fixed set of vocabulary, but make the model to be able to generalize to open set of vocabularies beyond the training data. Like you can see here, although the model is not trained on the bookshelf class, but it can still be able to recognize that class. So to achieve this goal, a very natural solution may be that we can ask humans to collect data to annotate different categories, right? But 3D is different from 2D, because for 2D images, we can get these free labels from the internet. But in 3D, the data on the first hand, the data is limited, and on the other hand, it's not feasible to annotate all the 3D data for different categories, right? It's very time consuming. There are no free labels on the internet. So we are inspired by the success of current foundation models that are trained on ImageNet, that they can actually recognize open set vocabularies, right? Like in this here, given one image, if we feed it into a vision language foundation model, they can give us very accurate descriptions regarding the semantics and even their functionalities. So actually, in many of the 3D harvesting pipeline, the 3D are naturally from images, and if we have 3D, we can also render images, right? So in this work, we are thinking about whether we can use this image as a bridge to distill knowledge from pre-trained 2D image-to-text foundation models to allow the 3D models be able to be trained on open set vocabulary and have the open world capabilities. So the key idea is we given a 3D scene, we can use them to render multi-view images, right? And then we can feed these images to vision language foundation models, and these vision language foundation models can give us very detailed descriptions of the corresponding images, consisting of the corresponding class and even the materials, really in a very open set of vocabulary space. And this, by using this image as a bridge, actually we can trace back the 3D areas that this image is coming from, and to relate 3D with corresponding descriptions, right? So after doing this, we actually can build this point and language pairs of data. So this language actually have open world, open set vocabularies. And by using this point language paired data, we actually can you leverage them to train a model, that this model will be trained on open set vocabulary. Like then we will, given this language and 3D pairs, we can leverage contractive learning to learn the semantic embeddings of the 3D point cloud, and to make it to be aligned with the corresponding language embeddings from these language descriptions from 2D foundation models, By doing this alignment using contractive learning, we can do an open world inference that we can feed any labels into the system and to see whether there is one label, to locate the current areas that corresponding to this semantic category. So so these are some examples. So actually, our work can generalize to recognize like these categories. They do not exist in the training data set, but our model can recognize them successfully. And also, like for these two classes that is actually referring to similar things, using different words, our model can also locate the specific areas referring to these semantic categories. And this is more visualizations. So all these categories do not exist in the training data set. For example, library and working office, they are actually not a single objects, right? They are an area, but our model can still locate the corresponding areas that are very relevant to the corresponding class. So as we are doing open world scene understanding tasks, for scene understanding tasks, we actually want this model to localize the objects in a very detailed manner, its corresponding locations, right? So in our follow-up work, we actually are thinking about to use more powerful region-level vision language models to help us to build a fine-grained 3D and point associations to make this 3D, make this language supervision to be more accurate, to be more closely related to the corresponding areas related to that. So this also help us to get better results. So you can see, so these are the results from our approach, and this is the the results from using fully supervised training. This is already significantly improved compared with the previous approaches. And we can also do open world 3D instance segmentation, like this is the result. So why we care about open world understanding? Because if we have the model has this open world understanding capabilities, this actually can help us to translate this 3D information into a language space, and then we can leverage more powerful models like large language models to help solve more complicated tasks. So for example, in this example, if the user gives some inquiry, so we can leverage language model to decompose this into different steps, and for each step there are corresponding objects that need to be located. Then we can leverage the open world instance segmentation model to locate these corresponding objects. So in this application, mostly this vocabulary space would be in an open set. So this open world capability is very important. Okay. So far, what I have discussed about is about perception and understanding, which is we already have the data there. We would like to interpret them to extract 3D information or to understand their semantics. So beyond this perception and understanding, another task that we are exploring is about generation. So the goal is that we would like to recreate the 3D or 4D world in the digital space. This can be utilized for robot simulation, gaming, VR and AR, and so on. So as we all know, for 3D tasks, data is very important, right? It's very difficult to get a large amount of data compared with 2D tasks. So for 3D generation, a very popular approach is that whether we can distill knowledge from 2D diffusion models to optimize the 3D representation, to make it to be able to fit leverage the priors from 2D diffusion models to being able to optimize the 3D representation to have a 3D object. So there is a very popular approach called score distillation sampling. This is typically done by distributing the detailed knowledge from 2D foundation models to optimize the 3D representation. So its formulation can be decoupled into two parts. So the first part is to enforce the rendered image from a 3D representation to be real according to the 2D pre-trained diffusion models. And another part is to make the rendered images to be aligned with the test prompt. We call this as a classifier guidance. So when this approach was firstly proposed, so these two objectives are incorporated in the formulation. But we actually, in this work, we found that the most critical component is this classifier guidance. That is to make the rendered images to align with the test prompt. Well, this term doesn't contribute to optimization. So this finding has motivated us to remove this from this training objective, but using this classifier guidance as the solo guidance to distill knowledge from 2D diffusion models. Although this is very simple, but we found it actually delivers much high quality results, and it's offer like seen here. So all these objects are from our approach, and also it offers more flexibility for 3D editing tasks. So I will not detail it here. So this is about text to 3D generation using 2D prayers. But in some specific areas, we may have a lot of training data, right? We can also afford to train model for specific tasks. Like here, for this texture synthesis tasks, given a 3D mesh, we would like to add diverse textures to this 3D mesh. So when we want to represent, so for this problem, a question is how can we represent the textures so that it can be better processed with models, right? So a natural representation for mesh textures is to use the UV map, right? This is a 2D map, and it can offer high resolution synthesis. But if we directly use this UV texture as a representation, it actually it will break the 3D consistency and 3D connections of different areas, right? Because this 3D consistency is broken in this UV map. And if we only use this as a representation, we can find the synthesis results will do not have much a good 3D consistency. So in this work, we trying to use this point cloud as the global 3D representation to enforce consistency for synthesis and to combine them together. So we propose a new computation block that drawing this UV representation for high resolution synthesis, and also it interleaved with point block to add 3D consistency for texture synthesis. Then building on this block, we build a foundation model and it is trained with the diffusion objective to allow it to synthesize high quality 3D textures. Let's see some results. So this is the synthesized results. No. So all these are the synthesized results, and we can also to combine multiple synthesized results into a scene to create a virtual environment like here. You can see here. Okay, so let's move on. Okay, so far what I'm talking about so far is mostly about static things, and our real world is really dynamic, right? So can we do better 4D simulation and 4D modeling? So in this work, we actually propose a new representation for 4D simulation. That is the idea is based on Gaussian splitting. So we would like to make the 3D Gaussians to be able to model dynamic scenes. So in this work, we actually is inspired by the sparse nature of real-world motions, and we introduce sparse control points for learning the motions of 3D Gaussians. So the idea is here, given the 3D Gaussians, we introduce a set of control points, and for each of the control points, we will leverage a multi-layer perception model to learn neural network to learn a time-varying 6-stop transformation for each of the control points, and then given a Gaussian, given a 3D Gaussian, it will look at its key neighbors, and its motion will be interpreted by its key neighbors. The motion of its key neighbors, and then each of the Gaussians can move in space, and then given a new camera view and given a new time step, then it can render images. And by comparing the images with the given training videos, this representation will be optimized. Both the 3D Gaussians and these control points will be optimized, and the control points will be put and densified to adjust itself to different motion complexities. And after optimization, we actually found a very surprising fact that we can use around 500 control points to drive the movement around 100,000 Gaussians. So these control points are essentially learning a sparse set of motion trajectories, okay, and this underlying motion is really sparse. And what this brings us, if by introducing these sparse control points, we actually add more structure to this Gaussian representation, and this can allow us to perform editing on the reconstructed 3D motions. So, for example, by replacing the MLP as user-controlled motions for the control points, we will allow users to control the motions of the 3D scene. Let's look at more results. So the top row is the result from reconstruction. You can see their rendering quality is very good, and the bottom row is the edited motions. So you can see, although all these motion patterns are new from the training data set, the rendered results are still very well. See, here are the more applications. This is essentially a static thing. By introducing sparse points, we can also make them to make natural motions. So actually, so this 4D representation is not limited to modeling 3D scenes, but it can also be applied to video editing or video generation tasks. So in this work, we actually tried to model a casually captured video using a Gaussian representation. So by doing analysis on this Gaussian representation, we can perform many applications like tracking, consistent depth feature refinement, video editing, stereo view synthesis, and interpolation. So let's just look at some results. By tracking 3D Gaussians in the 3D space and project the tracking onto 2D, we can perform this tracking. And by lifting this depth attribute or the feature attribute onto this 3D Gaussian representation and reproject them into 2D, we can make them to be more consistent across time. And this is by removing the corresponding the area correspond the Gaussians corresponding to these areas and represent this edited 3D Gaussians to 2D videos. We can achieve by moving objects or adding new objects into the scene. So they actually can, the 3D representation can actually help us gain a lot for consistent editing. So this is more results. By doing stylization and on the 3D Gaussians and reproject them onto 2D, we can also achieve consistent stylization of the videos, and by adding this new content onto a video. So this is to do interpolation of the videos. This is also achieved by doing interpolation of the Gaussian along these Gaussian trajectories and reproject them onto 2D. We can achieve better video, a good video interpolation results. And this is as this representation is a 4D representation, we can also synthesize the stereo views and create a stereo view videos like here. Okay. So this is mostly about what I will talk about today. Actually, our focus is on two major parts. One part is for 3D perception and 3D world simulation. So we would like to find good representations that can help us to turn these videos into a 3D world model, and we also would like to make it to be editable and to be interactable. And on the other side, we also care about understanding, reasoning, and action. We develop new approaches to enable machines to be able to understand the open world vocabularies, and also in the future we will explore whether we can unify understanding, reasoning, and action. And these two parts are actually interconnected. So they are connected by the agents. So we can, with this 3D reconstruction and word simulation, we actually offer the environment for agents to be trained, and then they can be trained to have better understanding and reasoning capabilities. Then they can be better interact with the world. Okay. So this is my students. All these works are from their hard working. So this is the end of my talk. Thank you.
Okay, thank you, Professor Qi. A great talk. So for myself, I have two questions. So I will ask first. So actually in your talk, I think it covers different kinds of 3D representations, like from the very beginning of the depths, and also the combination of SDF and also 3D JS. And then you talk about the mesh texturing, right? And also for point cloud for the 3D scene understanding. So there are many 3D representations. So my question is that do you think is there a unified 3D representation that are suitable for different kind of task? Or I mean, maybe not currently, or maybe in the future, a unified 3D representation?
Yeah, I think it's a very great question. So actually, I'm also thinking about this part, but I think for 3D it's actually very different from 2D, because different applications actually will have different requirements. For example, for some applications we may require speed, for some applications we may require high quality results. So I actually think for different, and also for different types of data, for example, objects or scene level data, different representations also differ a lot. But I think it's very, so from my current perspective, I think it's very difficult to get a unified representation to tackle different scene scenarios and also to tackle different tasks. But it may be in the future we may have some hybrid representations. So for example, like this depth information is very easy to use to model scene level, model scene depth information actually gives us very accurate. That would be more easy to be estimated from images and so on by leveraging foundation models, right? But if we want to turn it into a 3D scene, we can actually use this depth information as a supervision to help us to reconstruct this scene into a 3D space like a Gaussian and so on. Maybe that would be help us to make this representation to work well by combining the advantages of different representations.
Okay, thanks. And then my second question is also about the representation, but for robotics. So in your last slides, in the future work, you mentioned that we can do the 3D perception and also the understanding for robot, and also I think robot is a very important application for 3D vision, and I think it plays more and more important, right, with the development of embodied AI. So as far as I know, right now for robotic vision, they still use some very traditional 3D representation like point cloud, or even 3D occupancy or something like that. So actually for ourselves, we try to utilize the recent 3D neural representation for robotic tasks, but we found that it's hard, and sometimes because normally like 3D JS, even though it's fast for rendering, but it's not efficient enough for 3D perception. Actually, you need to do the online optimization, something like that. So I'm wondering, so what's your opinion about the 3D or the recent neural 3D representation for robot learning or robot vision? Yeah.
Yeah, I think that's also a very great question. So I think there's two. I think there are two parts that this 3D representation may help. One is for offline simulation. So actually, with this 3D representation, we actually can turn videos into a virtual 3D environment, and actually we can also make the environment to be interactable, so that they may be very good 3D assets or resources for training robots. Because currently robot learning also their data issue is the most critical issue, because the current simulation for the simulator they lack the real world diversities and complexities. But if we can turn this real world into a virtual environment, we may offer more diversity and complexities and bring real world into simulation environment. This is one part. And for the second part, if we are talking about if we want to use the 3D representation to enhance robot intelligence, I think this is also very critical, because for human, we actually have some virtual memories. So for that part, I think in the robot community, actually people are still largely ignored, because I think for the robot community, they are mostly thinking about to build vision language foundation models, vision language action models, and so on. But actually, we also have done some experience. We found that actually many mistakes of the robot from the vision language action models is from the lack of 3D information of the model, because the current vision language models do not understand 3D pretty well. I think a potential direction that may be explored is to use this 3D representation to build the memory, to build somehow a memory of the robot. And in this part, actually, it just serves as a map. Like if you have a room or a large scale scene, we can use this Gaussian to gradually to build the memory. And if the robot would like to make actions, it can retrieve from this memory, and this can augment the information, especially for the 3D spatial relationships of objects and so on, to make it to do better action and planning. So this is my thought. These two parts, I think these 3D representations are very important for robots. But actually, honestly speaking, I think they are not well explored, and I think there is still a long way to go. Yeah.
Yeah, actually, a very interesting thought. Actually, it also answered my another question. So, previously I thought whether we really need 3D representation for robotic tasks. Like there are many, like some recently there's some all kinds of foundation model, like navigation foundation model. They didn't utilize any 3D representation. They just given the input videos or even image, they can generate the control signals. So as you said, yeah, I think 3D representation really, I think plays also important role for robot. That's also my opinion. Okay, thank you for your answers and also for your great talk. Okay, maybe due to the time, I think we can switch to the next talk. Okay.